Hello, welcome to another module in this massive open online course. So in this module, let us start looking at another new, in fact revolutionary and path breaking development or technology, and that is of compressive sensing, alright, which has really revolutionized signal processing. So what we want to look at is an overview of compressive sensing, or also known as compressed sensing, and its relation to the optimization framework that we have looked at so far. So this is its a latest and very significant path breaking development or path breaking technology in signal processing, and its applications are everywhere, even in communication, biomedical signal processing, so on, in many domains. Okay. And to understand compressive sensing, let us start by considering a signal x bar which is unknown. Okay. X bar is an unknown signal, and this has to be therefore either estimated, since this has to be unknown, either estimated, or you can also say recovered or reconstructed. There are several words for the same. If it is an image, then we say the image has to be, the unknown image has to be, the original image has to be reconstructed. Okay. So, let us say this x bar is an n dimensional signal vector, it is a signal vector which is x1, x2 up to xn. This is an n dimensional signal vector. And how do we estimate this n dimensional signal vector? Naturally, we have to make some measurements. Okay. So, we make measurements for the signal vector, this unknown signal vector x bar, in order to estimate the signal vector x bar. So, that is basically we are sensing this signal vector. Okay. So, that is part of this compressive sensing. So, we have to sense So, you have to sense this in order to estimate, and therefore, what we have is we have this y bar equals phi times x bar. So, we are measuring, or we are, this is your observation vector or your sense. So, you are sensing this vector, and these are your observations. Okay. Y bar is your and this becomes your sensing matrix. Okay. And this can be written as, let us say we are making m observations. So, we have y1, y2, ym, this is equal to phi 1 bar transpose, phi 2 bar transpose, so on, phi m bar transpose times your let us write this dimensions suitably so that it is clear. So this is phi 1 bar transpose. The different rows are phi 1 bar transpose, phi 2 bar transpose, phi m bar transpose, because this is m rows and this is the vector that is being sensed. Okay. So this is your matrix phi, this is x bar, this is the observation vector y bar. So m is the number of observations. Okay. This quantity m equals number of observations, and x1 x2, and now these phi 1 bar phi 2 bar, or if you call them phi 1 bar transpose phi 2 bar transpose phi m bar transpose, these are the rows of the sensing matrix, and therefore now, so what are we doing? We are making these m observations y1, y2, ym through this sensing matrix phi. Alright. So each observation you can think of it as a projection of this vector x bar. Okay. So what you are doing is you are forming phi 1 bar transpose into x bar, that is one observation, phi 2 bar transpose x bar. So each of these observation is a projection of this vector x bar on a row of this sensing matrix phi. So if you look at this, you have, and you can clearly see this, you have yi, that is ith observation, equals phi I bar transpose x bar. So this is ith observation this is projection of x bar on row phi I bar or phi I bar transpose. So each measurement is basically a projection of the signal vector x bar on on a row of the matrix phi. And now since there are m observations and n unknowns, this matrix phi is an m cross n matrix. This is an m cross n matrix, and naturally if you look at this, we are trying to estimate the signal vector x bar, number of observations is y, number of observations is m. So you can say m is the number of observations or measurements. So m is the number of and n equals the number of unknowns. Okay, and therefore this is a system of equations with m observations or m nodes or m equations. M is the number of observations, measurements, or m is the number of equations, and n is the number of unknowns. And from linear algebra we know that in order to recover x, which is a vector of size n, you need at least n equations to uniquely determine x. So m is the number of measurements, which is the same as the number of equations. N is the number of unknowns or the variables. From linear algebra we know to uniquely determine x bar we need m greater than or equal to n. This is what we need. And conventionally, in conventional framework, we have m equal to n. Okay, and how do we do that? If you look at that, that means we have these n observations y1, y2 up to yn, which is simply the identity matrix So, typically what you have is you are simply sampling the signal. That is, you are simply, for instance, let us say you have a time domain signal, you are simply sampling the signal. Okay, at each instant you are taking a sample, or let us say you are an image, you are sensing each pixel via a sensor. Okay, so for a signal with n samples, all right, you are making n measurements. Okay, this is typically what we do. We have a signal of length n. We make n. So, for instance, the signal is in time domain. We make n different at n different instants. We sample the signal at these n different instants, n measurements, and from those measurements we recover the signal. Okay, so these are the samples. So you can say these are the this is the signal, and these are the samples, okay, in time or space. For instance, for an image, these can be in space. So these are sampling. So this is time or this is temporal or spatial sampling, you can say. You can say this is temporal or spatial sampling. This is temporal or spatial sampling, and we are making one sample per one measurement per sample or signals. One measurement of per sample or signal value. Okay. Now, and therefore, to uniquely determine, we said to uniquely determine the signal with n samples, we need at least m greater than or equal to n. We can choose m equal to n. Okay. Now, however, consider the following thing. Let us take a simple example. Consider a typical image, for instance. Now, the image equals, let us say it is 256, it is a small image, it is a 256 cross 256 pixel image, and let us say it is a color image, implies you have color image, that is RGB, implies for each of these RGB components you need 1 byte for each pixel, which means 1 pixel 3 into 8, that is your RGB 3 into 8 equals 24 bits, 24 bits per pixel. This implies the total number of bits per image the number of bits per image is 256 into 256 into 3 into 8 bits per pixel, which is equal to, if you look at this, comes out to be roughly 1.58 MB. Okay, so if you look at each image, if you just look at the raw image, the number of bits required to store a raw image, then you have about, for a simple image, that is 256 or 256 pixels. Of course, images nowadays have much higher resolution, but let us consider a simple example, a 256 cross 256 resolution, which means you have, and with a color image, that is you have 1 byte for each of the components RGB, and so 3 components and 1 byte for each. So 3 into 8 is 24 bits per pixel into 256 into 256, so that gives you 1.58 MB. Okay, and however, So that is, however, if you look at the size of a typical image on your phone or your computer, the size of a typical image file would be around 30 to 40 KB or at most 50 KB. So size of typical image this is, let us say, 50 to 60 KB only. Okay. Now, where is the difference coming, that is, where is the difference? So from a 1.5 MB megabits you are coming to 50 to 60 KB. So where is what is happening to this huge size, this image of huge size? How is this possible? How is it that you are able to get an image, store an image at such a small size, even though the raw image has so many bits? The obvious answer to this is that image, instead of storing a raw image, this image is being significantly compressed in size in terms of the number of bits. Okay. So typically for image store, so how is this possible? This is possible through compression. Okay. For example, you have JPEG, GIF, these are various formats for compression. Okay. So what is this paradigm for signal processing or compression, and this can be represented as follows. Let us consider a simple example. Let us say you have a image which is 1.5 megabits. Okay. What we are doing is the following: you are first sensing this image. So this is a large image, which implies you require a large number of sensors. Okay. This is your number of observations also. If you look at the earlier model, this is basically n. Okay. So basically this is conventional. Okay. So which means the number of sensors required is n. So image is of size n. You have a large number of sensors of size n. This is your conventional sampling or sensing. That is, you are taking one sample, you require one sensor per sample. However, interestingly, or rather strangely, after sensing, you are compressing. That is, you throw away significant amount of data. So what you are doing is, strangely, you are using a camera. For instance, you have a camera, all right, in your phone, or let us say a separate standalone camera. Then you are sensing it at this huge resolution, all right. For instance, you are sensing it in terms of the megapixels. Okay, you have a camera which has a resolution of several megapixels. You are sensing it, and ultimately the image, the raw image that you capture, or the raw signal that you capture, has a huge size, which is captured using a large number of sensors. All right. But after the capture process, you are throwing away a significant amount of data to compress it, which means basically you are using a large number of sensors. That is, your original device is very expensive because of the large number of sensors, but at the same time you are not able to leverage, or you do not need this, because you are throwing away a large amount of data, because the compression is coming after the sensing process. That is the important aspect. The compression here is coming well after the sensing process. That is the important thing to realize here. In this conventional paradigm, you have compression well after the sensing. Compression is coming well after the sensing process. This leads to a wastage, this leads to a large number of sensors, wastage. This leads to a large number of sensors significantly. Implies the resulting system is expensive, implies the resulting system is extremely expensive. Now instead consider, consider this paradigm. You have an image, consider this paradigm, you have an image, you perform m measurements much less than n, that is number of sensors m is much less than n. This is termed as compressive sensing. So you are not using number of sensors that is equal to, m is not equal to m is not greater than, in fact the number of sensors m is much less than, much lower than the number of samples or the size of the signal vector n. So basically while the sensing process itself you are compressing, it is as if for a 1.5 megabit image you are making only 60 kilobit of observations roughly, alright. So you are not sensing and compressing, but compressing while sensing itself. Now therefore, now since you are compressing while sensing, later you have to recover the signal or reconstruct the signal. So first instead of sensing and then compressing, you are compressing while sensing, and then you can perform signal recovery. Signal recovery to extract the original signal. So this is the idea. So this is very few measurements followed by signal recovery, very few requires very few sensors. So you are performing compression during sensing or compression together with sensing. This is basically nothing but the framework of or let me just write it in block letters to emphasize this. This is basically the framework of compressive sensing, which results in a significant saving in terms of cost, significant saving in terms of the number of sensors, because you are making very few measurements in comparison to the size of the signal. Now naturally that implies also that since the number of observations is less than the number of signal samples, remember this is similar to remember we said the sensing process is similar to solving a system of linear equations. M is the number of observations, n is the number of signal samples. So we need m greater than or equal to n. Now naturally if m is less than n, one cannot uniquely determine the signal vector x bar, because linear algebra results still remain the same. So therefore one has to come up with some ingenious techniques or some new ideas to reconstruct the original signal x bar from this compressed or compressively sensed signal, alright, y bar. Now what are those techniques? First, how do you sense the signal in a compressive fashion, and what are those ingenious ideas that you use for reconstruction? That forms the basis of compressive sensor. In fact, this is where the path breaking ideas come in, that is, how do you reconstruct this signal using a much fewer number of sensors or much fewer number of observations in comparison to the total signal size. Okay, and it is not possible to do it using, of course, if you look at the results in conventional linear algebra, it is not possible to do it, therefore one has to come up with a new framework, and that is where the optimization aspect also comes in, which is what we are going to look at in the subsequent module. Thank you very much.